theorem. So it's mu times t plus 1/2 variance times t squared. Okay, that's the form for the momentary radian function of normal distribution.
Is that all in the exponential or not?
This is e to this part and then times e to this part. So this is the exponential here. This is in the exponent
The whole
there.
thing is the
and
exponential?
here the whole thing
Is
the
exponential.
This is the exponential. So I just multiply these terms together, which means I add the exponents. So here the exponents are everything. All right. Okay, so with this, we'll stop with the momentary radian function. We can talk about joint momentary radian functions, but I don't think we need to know that. All right.
I was really looking forward to that.
All right. So let's move on to the central limit theorem. As I said, you have two very important theorems at the heart of probability, and one of them is called the law of large numbers, the other one is the central limit theorem. So what the law of large numbers says, normally you should first learn the law of large numbers and then the central limit theorem, but I'll state the central limit theorem first. With the law of large numbers, the idea behind it is that if you take the average of something, say if from a population, you sample people, and say you're interested in heights, and you take a large sample. As your sample size increases, the average value will approach the population mean value. Okay? So that's called the law of large numbers, because on average, if you sample many times, you will approach the mean. Okay? That's the idea behind it, which is why it makes sense to look at large samples, because the larger the sample it is, the closer you're getting to the true mean value. Okay? And I'll talk about that more on Monday. Now, in central limit theorem, the idea is how much does each of these samples that you take. So let me refer to them as random samples. So you haven't yet actually sampled, but if you did take a sample, say the ith sample, so you have x1, x2, xi, and you look at the deviation. So you're sampling from a population which has some mean. Look at its deviation from its mean. Okay? If you add up all the deviations, okay, these deviations, the sums of the deviations from the means, start, they get distributed like a normal distribution. Okay? So on average, the deviations from the mean, when you take a very large sample, should go to 0. Okay? Because maybe I should write it like this. So this is the average. Right? So x bar in the long run will approach mu. But I look at x bar minus mu. As n gets larger, x bar minus mu should become 0. Okay? But before I approach the value 0, so that's as your n goes to infinity. But before that, okay, so x bar should approach 0, right? But I can look at its distribution about the mean value mu. Okay? Or basically, you know that this error x bar minus mu, when I look at this error, this minus mu, gets distributed like this. That is, on average, so most of these errors would be 0, and you'd have few very large errors and few very small errors. Okay? So basically, I'm going to look at, so xi's are measurements, okay? And I look at the deviation of these measurements from the mean value, okay? And I'm going to add up, so think of these as errors. Okay? If I add up these errors, on average these errors should be close to 0. Okay? And you have few that have very large positive error or very small positive error. Okay? So basically the central limit theorem is something about the distribution of these errors. Okay? And well, if I just keep adding this up, this could blow up to infinity. Okay? So you have to do something which is called scaling, and the right way to scale it is by sigma squared.
What was that statement you said? Like very few will have large positive errors or small positive errors. So I'm just trying to understand the axis of that graph again. What's the graph represent again?
So when you calculate this, so xi's are random. So when you calculate, this is some random value, right? Xi's are random. Okay. Okay. So when I calculate this quantity, this is some random quantity. Okay. Most of the time, this value will be close to 0 when I calculate this sum. But sometimes, maybe but this is going to be very unlikely that I keep sampling things that are larger than mu. In which case, if I add up these errors, they're all positive. Okay? So it's very unlikely that you have a very large positive error. Right? So I mean, I can't consistently be picking out people who are way taller than the mean heights of the population, right? Okay? Because chances are it will average out to about 0. Sometimes some people are higher than the mean, some people are lower than the mean. So this, typically, there's a higher probability that it's close to 0. There's a small probability there's a very large number. There's a very small probability that I've always sampled people that are taking values less than mu. Okay? So this, it makes sense, I mean, it intuitively makes sense that these sort of errors, the deviations from the means, are getting distributed like that. All right.
But to the right, we have a positive error. To the left, we have a negative error.
Yeah, so this is the identity of positive error, this is the identity of negative error, this is 0. And I'm saying that basically as n goes to infinity...
What is that one again, the error?
This, I would think of this as the error. Error in the sense how much it deviates from you. Okay? Or you can think of it as, supposing there's a manufacturing process and there's the manufacturer claims that everything has a standard size. Okay? Say this pen is supposed to be, what, 3 inches long, 4 inches long, something like that. But maybe there's some amount of deviation. Okay? Well, with this, I don't think it's likely, but let's take things like candy bars. Okay? Okay, so here, basically, if you take a very small sample, very likely most of them are going to be, so your n is small. It could happen with a fairly high probability that xi minus mu something, the summation of xi minus mu is large. That is, you're always taking values above the mean value. Yeah.
Can you explain square root of n? If you were just doing like z, wouldn't it just be xi minus mu over sigma? I don't understand what square root of n is.
Okay, so yeah, we will get to why we're scaling by sigma. Okay? The whole idea is, okay. So now let's come to, so let me rewrite this. This becomes summation I equals 1 to n xi minus n mu over sigma square root of n. Okay, so let's see, why is it sigma square root of n? Okay. Let's look at what is the mean of summation of xi's. I'm getting to sigma square root of n.
I'm talking about the n.
Yeah, minus n mu. If I sum this, I'm summing this n times, so minus n mu, right? All right. What is the mean of this? This is just going to be one. This is just one of the properties that we have. So this is just going to give you n times mean. because each of the expected values xi's is mu. What is the variance of this? So the variance of this is, I'm taking xi's to be independent, so I'm just sampling independently. Then this becomes I equals 1 to n variance of xi. And I'm denoting the variance of the population by sigma square. So this is summation I equals 1 to n sigma square. So this gives me n sigma square. So that means as I sum up things, my mean, of course, of summation xi is becoming n times mu, which makes sense. I'm adding up these values. And the variance is also becoming very large. Okay? So the more numbers, more values I add up, the more variation I see. And because this can be very large, this could either, blow up to plus infinity or go down to negative infinity. So to avoid that, as n goes to infinity, to avoid that, I scale by the standard deviation. Okay? This will ensure that when I take this limit as n goes to infinity, it doesn't go to either 0 or infinity. Okay? So this is the right scaling. And this is what's interesting about the central limit theorem. It says that there are two things it says. That the right scaling is sigma square root n. Okay? And the reason is because the variance is n sigma square. So when you take the square root of that, is square root of n sigma. And the other interesting thing that the central limit theorem says is that this approach is a Gaussian distribution. And you can see that if you thought of these things as errors, it kind of makes sense that it should be Gaussian distribution. Now, this is central limit theorem. You have other kinds of limit theorems. So if your xi's are some strangely behaved random variables, if they're not independent, this, first of all, sigma square root n may not be the right scaling. Okay? You might have to scale by something else. And the limit may not be Gaussian. It could be something else. Okay? But that is when you get into like research level probability theory. So for most of the time, what happens is this. That is, you scale by sigma square root of n, and the limit as n goes to infinity is Gaussian. So this is called the central limit theorem. Now let me write down the statement of the central limit theorem. Okay, so what you're basically saying is the sum of a large number of independent random variables, and this is important, these random variables need not be normal. If they are normal, then that's trivially true. Distribution that is approximately normal. Let me actually write down the proper statement. Write the statement here. And this is the central limit theorem. It's a CLT, I mean central limit theorem. Let x1, x2, etc. be a sequence of independent and identically distributed distributed random variables, each having mean mu and variance sigma square. Then the distribution of plus x2 sum to n. If I subtract the mean of that is n times mu, we just check that the mean of the sum is n mu, and I divide by the standard deviation. The variance of the sum is n sigma squared, so the standard deviation is square root of n sigma. Then the distribution of that tends to the standard normal as n goes to when I say the distribution of that tends to this equation, what I mean is the following, to be precise. The probability that, if I'm looking at the distribution of this, I'm basically looking at the probability that sum minus n mu over sigma square root n, the probability that this is less than or equal to a, this converges, or the limit of this as n goes to infinity, converges to a distribution function for standard normal. So what is the distribution function for standard normal? Integral negative infinity to a, e to the negative z squared over 2 dz. So it's just the integral of the density of the standard normal from negative infinity to a. This is just so the probabilities of this, that is the probability distribution of this thing, approaches the standard normal.
Is there a shorthand way of referencing that particular scenario? You know, like if you were to write the probability of something, how would you write that? You know what I mean? Instead of writing out x1, x2 to xn every time?
Oh, you can write summation.
Okay. Oh, of course.
So you can see that I guess I'm going to skip the proof because it's going to take some time, and I'd like to get to some problems involving central limit theorem. But what I'm trying to prove here is that this random variable, as n goes to infinity, its distribution approaches standard normal. Okay? What do you think would be a good way to check that? Now that we know that moment-generating functions determine a distribution, maybe if we the idea of the proof is basically this. Let me call Zn this random variable, x1 plus x2. And so as n increases, we take a larger sum minus n mu over sigma squared n. So this depends on n. What I would do is calculate the moment-generating function of this. Calculate means I write down the expression for that, and prove that the limit of this, that this goes to the moment-generating function of standard normal. So basically, I want to show that the limit as n goes to infinity of this random variable is the standard normal. What is it? It's e to the mu t, mu is 0, and then 1/2 sigma squared is 1, so e to the t squared over 2. So the central limit theorem, basically the proof, the main part of the proof is checking that the moment generating function for this sum minus n mu over sigma squared root n converges to the moment generating function, this moment generating function. Okay? And if it converges to this function, We know that this is the function, this is the moment generating function of standard normal. So that means in distribution, this is now distributed as standard normal as an equation. Now, in practical terms, when we want to use the central limit theorem, the reason why it's useful is because now, no matter what the distribution of xi's are, I know if I take the sum of these xi's and I subtract n mu divided by sigma square root of n, all I need to know is the mean mu and the standard deviation. And then I know that this, even when n is not infinity, but when it's pretty large, that this is going to be approximately normally distributed. And that's useful because I know how to calculate probabilities for normal distribution. We did do a special case of the central limit theorem, and that is when we talked about normal approximation to binomial. Okay. Now, why is that a special case of this? So I said for the normal approximation to binomial, if x is xn is binomial np, I said that xn minus np over will approach normal, right? Now, why is this? I can just use the central limit theorem to prove this, but that means I need to write this as a sum of independent identically distributed random variables. But there's something that we already know now, that if I have, if each of these are binomial 1p distributed, then this is going to be binomial np. Because we just proved earlier today that if x was binomial np distributed, y was binomial mp distributed, x plus y was binomial, this added up. Okay? So your n and m added up. So if I take n binomial, basically Bernoulli random variables, and I take their sum, the sum of n of them, I get binomial np. Okay? So now any binomial np random variable can be written as the sum of IID, that's independent identically distributed Bernoulli random variables, and subtract the mean, which is n times mu. Mu for this is just p, okay? And sigma is just p square root of p times 1 minus p, so they're exactly the same thing. And that's why we did this for binomial when n went to infinity. So now whenever you can write your random variable as a sum of independent identically distributed random variables, you can always use a normal distribution approximation. So you can always use the central limit theorem. Typically, if n is greater than or equal to 30, of course it depends on what your initial distribution is. If it's binomial, you check if np is greater than or equal to 5, np is greater than or equal to 10. If it's not binomial, just check is n greater than or equal to 30 and then use the normal approximation. Even if it's less than 30, you can use the normal approximation. It may not be that accurate. So clearly when n is larger, it's better.